The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar. This is the fourth webinar in our Cathodoluminescence series and is titled Cathodoluminescence Explained, Episode 4, Improving Spatial, Spectral, and Angular Resolutions. With that, I'd like to introduce our presenter today, David Stowe. David is the product manager at Gatan, responsible for cathodoluminescence products. He has almost 20 years of experience in CL, initially using CL spectrometers to characterize the light emission from crystal defects in silicon, to gain his doctorate from the University of Oxford before joining Gatan as an application scientist and more recently as a product manager. While at Gatan, he has worked collaboratively with researchers in a wide range of applications, developing new analysis methods and CL instrumentation for scanning and transmission electron microscopes. Before we start, please note that you may submit questions at any time via the questions pane on the GoToWebinar dashboard. At the end of David's presentation, he will answer these questions as time permits. Anything that is not addressed will be answered offline. And with that, I will hand the webinar over to David.
Thank you. Hello, everyone. Welcome to episode 4 of Cathodoluminescence Explained. Improving spatial, spectral, and angular resolutions of luminescence data. So this is episode number 4, so I'm going to give a very brief overview of the CL experiment, more particularly the hardware involved in it. And if you want to know any more information about cathodoluminescence, please go back and review the earlier episodes that we've done. There's lots of information contained there, and there are links available from our website in order for you to be able to view those previous. So in today's presentation, really we are going to examine how we can use the experimental apparatus used in the CL microscopy technique, the electron microscope and CL detector itself, and how those operating parameters influence the resolutions that we have in various CL detector operating modes. Importantly, we will also have an understanding of how your sample itself influences the data that you collect. So, as a reminder, cathodoluminescence is the emission of light from a sample when it's been struck by a high energy electron beam. And typically we're talking about using the electron beam of an electron microscope, like a scanning electron microscope that I have schematically represented on the left-hand side, but equally it could be a transmission electron microscope too. And to those electron microscopes, we attach some sort of CL detector. Here, this is the Monarch detector from Gatan, a spectroscopy, imaging, and polarization analysis tool. And it allows you to analyze the light that's collected or that's emitted from the specimen, and allows you to correlate the optical and electronic properties that you get from that light information with the chemical and structural properties of the material and the other signals from the macro down to the nanoscale. So really, cathodoluminescence is a meeting of electron microscopy and luminescence spectroscopy. There are lots of forms of luminescence spectroscopy: electroluminescence, chemiluminescence, photoluminescence. Some you see every day in your lighting applications. So light-emitting diodes emit using electroluminescence. Many semiconductor materials are characterized using photoluminescence, and they are fantastic techniques for giving insight, or for creating real devices, and also for giving you insights into the optical and electronic properties of the material. Where CL differs from these techniques, though, is in two really important ways, and really important because it gives you interesting information that you can't get. First of all, the excitation of the electron beam is much greater than the energy of the emitted photon. And this allows us to analyze a very wide range of materials, including insulators like rocks, minerals, gems, ceramics, and other oxides. So we have a much more flexible system in terms of the material systems that we're able to analyze. But perhaps most importantly, the advantage of cathodoluminescence is that we have high spatial resolution, because we have this focused electron beam that we can focus down to sub-nanometer focus spots to interact with our specimen, and this is important in giving us spatial resolution that the other techniques simply don't have. So let's take a comparison on a sample. So this is, doesn't matter particularly what this sample is, but these are two images captured simultaneously. One on the left is a secondary electron image of a collection of nanowires deposited on the substrate, and the other is a cathodoluminescence map. And you can see straight away that the cathodoluminescence information gives you, or the cathodoluminescence image, the CL image, gives you completely different information to what we have in the secondary electron information. We shouldn't be surprised by that. We've already seen how CL gives you information about optical and electromagnetic properties rather than structural properties necessarily, whereas the secondary electron gives us topographical information. The other thing that's important to note, though, is that the spatial resolution of the CL image is not as good as the secondary electron image. And the question for that is, for users of the equipment, is this simply a limitation of the technique, or are there other things that we can do as the operators of these tools in order to improve our CL maps? Fortunately, there are lots of things we can do, and so we have a reasonable sized presentation to listen to rather than just saying no and being finished for the day. So let's take a slightly detailed look about how different methods of improving the spatial resolution of CL maps. Now, the luminescence process is a multi-stage process. So we shine an electron beam that has energy onto a sample, and the electrons interact with the sample in some way, and that energy is absorbed from the electron beam into the sample, and then internal processes happen that transform it into another form of energy, before finally a photon is emitted and the sample relaxes to the ground state. That photon gets emitted from the sample, escapes into a vacuum space for us to be able to detect. So there are many, many different steps and processes that take place in order for us to release a photon of light for us to be able to detect in our detector. So in order to be able to understand which one of these effects is the limiting factor, I'm going to walk you through this process on a few steps, because depending on exactly on the sample type, the limiting factor may be a different part of the process. So let's first of all start by looking at the very first step, how the electron and the sample interact together. So I showed you pretty much this slide at the start of the presentation. It's the schematic representation of the electron microscope and the CL detector attached to it, and it shows an electron beam focused down to a potentially nanometer-sized probe. What I glossed over on that initial slide was that actually these energetic electrons lose energy and as they penetrate below the surface of the sample and interact with the sample to generate the signals that we detect. And in fact, these initial electrons in our electron beam can have much, much higher energy than what they lose on each event as they transfer some energy to the sample. So we end up with the initial electron undergoing many, many scattering events. And so it penetrates potentially quite deep into the sample and spreads out. And this region in which the interaction takes place is called an interaction volume. And we're going to take a little closer look at that on the next slide to understand how these different signals, or where these different signals are generated from within this interaction volume. So here is a representation of our sample and an electron beam shone on it. The electrons have penetrated below the surface. They're losing energy as they do so until they finally come to rest. You can see that the electron beam penetrates down and spreads out sideways. Now, there are a number of different signals generated within the electron microscope. And we can broadly class these into two different types of signals. The first being associated with electrons, secondary electrons that allow us to look at things like topography, and backscattered electrons that allow us to look at atomic mass. But all of these signals have to originate from close to the surface of the material, within the top few nanometers or few tens of nanometers, because they need to be able to escape into the vacuum space in order for us to be able to detect. If they were generated deeper within the material, those electrons would be reabsorbed before they had a chance to escape the material, and so we would never be able to detect them. So these electron-based signals come from close to the surface. On the other hand, photon-based signals, like the light photons that we measure in cathodoluminescence, or the X-ray photons that we measure in energy dispersive spectroscopy, these come from much deeper within the sample because generally they're able to travel through the material and exit from much deeper within the material. So these photon signals come from much deeper, and as you can see at these deeper depths, the spread of the electron beam is of the electron. The region of the interaction volume is much wider. So the image resolution in the case of X-rays and light photons is limited by the lateral extent of this interaction. Here I've indicated the X-ray image resolution we should expect with an interaction volume of this size. And typically in a bulk material, it's of the order of several microns. So orders of magnitude lower resolution than is the case in the electron signals. It doesn't always have to be this way. So we've seen that the size of, or the image resolution in cathodoluminescence and X-rays are associated with the size of the generation volume, the lateral spread of it. Here is a cathodoluminescence image of a geological mineral captured with an accelerating voltage of our SEM set to 20 kV. And you can see that the image resolution here is about of the order of a micron, maybe a little bit better. We reduce the accelerating voltage, the electrons in that the initial electrons lose their energy much sooner, and so penetrate less far into the sample and have less chance to spread out. So the interaction volume is smaller, and you can see that this lateral spread of it is smaller, and so we have higher spatial resolution, as you can see in this image at 10 kV, and also at 5 kV. You see a significant improvement in spatial resolution as we move to lower accelerating voltages. But this is important, particularly when trying to make high resolution maps in geological minerals, that we understand that the key thing that's influencing the spatial resolution in our maps is this lateral spread. Now we generally have free control over the accelerating voltage we set in the electron microscope. And so we could choose any voltage we want between typically a few hundred volts and 30 kV. And we can quantitatively work out what we expect the image resolution to be by performing these simulations of how the interaction volume is formed within a material. See here, plotted on the same length scale, the three simulations that demonstrate the interaction volume under these three different microscope accelerating voltage conditions. And you can see as we reduce the accelerating voltage, we see this much clearer and sharper SEM or CL images. We can actually plot this and work this out, as I said, quantitatively for a range of electron energies. And you can see that on this log-log scale, it has this linear relationship. So at 30 kV, depending exactly on the type of material, we are penetrating between 2 and probably 8 microns, whereas at 1 kV, we're now down to an interaction volume size of about 10 nanometers to a few nanometers. So by going to lower accelerating voltages, we can dramatically decrease the size of our probe and get this improved spectral resolution. Well, that sounds very simple, doesn't it? So it sounds like we should always dial in a low accelerating voltage and just get the most beautiful maps that you can. However, it's not that easy. Here is from the same material. This happens to be a zircon, a polished zircon material, a CL map captured with an accelerating voltage this time of 2 kV, so quite low, especially for a geological mineral. You can see that we have actually very good spatial resolution. Here, this line that's apparent from a zonation within the material has a line width of just 40 nanometers. So we know that we have an image resolution better than 40 nanometers, which is about what we would expect with a 2 kV electron beam from the size of the interaction volume. However, it's immediately also noticeable that the image signal to noise ratio has been dramatically reduced. That's because we've got fewer photons being produced for every electron that we put into the sample. And we also have many more surface-related effects. So within this map, you can see scratches that are in the sample from the mechanical polishing that was used to prepare this sample, and they act to kill luminescence. And there are lots of other surface-related defects there that cause us to lose efficiency from our sample and get many, many fewer photons being emitted from our sample. Now, this is actually a relatively bright material. It emits a lot of photons for a given number of electrons. But even here, we've run out of signal to be able to produce nice maps. And in most minerals, the practical limit of how low we can turn our electron beam down to get our sharpest images is defined by the signal to noise ratio of the image, which really is defined by the sensitivity of the CL system that you use for a given. The sensitivity of the CL system is actually very important. Now, this understanding of the lateral extent of the generation volume is the key thing to understand for getting high spatial resolution maps for geological materials. If we now think about a slightly different material class, if we think about semiconductors, we have to think about other processes that take place within the sample whilst we are, or between the energy from the electron beam being absorbed and a photon being emitted. In semiconductors, what this means is that we have to consider minority carrier diffusion. So here are those. Here are three plots of the interaction volume size. This is Monte Carlo modeling, again, using this casino program from the University of Sherbrooke, and at three different accelerating voltages, and they're plotted with different length scales. So this is where electron-hole pairs are being generated within the sample, because that's the mechanism by which semiconductors absorb the energy from that initial electron beam. However, we now have a high concentration of carriers in this region, and they are subject to diffusion. They move around within our material before they have a chance to recombine and radiate and emit a photon. We must also consider the effect of minority carrier diffusion, i.e., what these electrons and holes do before they recombine to emit a photon. And for a given material with a diffusion length of, say, 200 nanometers, which is not uncommon amongst many semiconductor materials, you can see that minority carrier diffusion actually changes the distribution profile of where our electrons and holes are within our material, particularly at low accelerating voltages. So at low accelerating voltages, the minority carrier diffusion length has a very significant effect on the CL spatial resolution, whereas at high accelerating voltages used, it has virtually no effect with this diffusion length. So in semiconductors, not only do we have to consider the accelerating voltage used for the microscope, but we also have to consider what happens to carriers after they've been generated, i.e. minority carrier diffusion. So we can see this effect actually taking place when we look at maps of threading dislocations in, for example, gallium nitride. For those of you who don't know what threading dislocations are, effectively they're just they're crystal defects, one-dimensional crystal defects. And so they are the order of the atomic spacing, so less than a nanometer, probably just a few angstroms in line width. And they travel all the way through a crystal down from the surface, or in this map that I'm about to show you. So we would expect to see a black spot at the site of these dislocations because these dislocations act to kill luminescence locally. And we do that. So here is a CL map acquired at very low accelerating voltage so that the interaction volume is almost negligibly small. And you can see in this map that we have these black spots that we would expect. However, when we look a little closer, we see that these black spots are not atomically sharp defects, but actually have a physical extent of somewhere between 50 and 100 nanometers. And that is about the size of the diffusion length in this material. So we can see in this CL map that we are limited by minority carrier diffusion, or the spatial resolution is limited by minority carrier diffusion. So, should we ever expect to beat minority carrier diffusion as a spatial resolution in a CL map? Well, the answer is possibly, and that really depends on the structure of your sample. So, fortunately for us as microscopists looking to understand devices and defects at this nanoscale, when you have a material that's not homogeneous but is actually made of different materials, then the actual sample structure can start to prevent minority carrier diffusion. For example, if we look at this energy band diagram that I've discussed in a previous episode, you can see that electrons and holes flow into this different material, get captured, and so are no longer able to move about freely. It means that when we look at this cathodoluminescence map acquired from this material generally has a diffusion length of several hundreds of nanometers. When we do a line profile of that intensity, we can actually resolve layers which are just a few tens of nanometers thick, so 20 nanometers thick, and resolve between them. So it means that here, the thing that's actually determining our spatial resolution, not the size of the interaction volume, because we've been able to shrink it to a small enough size. It's not minority carrier diffusion, because our sample is capturing the electrons and holes and preventing minority carrier diffusion. It's actually the sample itself. So the sample itself is the thing here which is limiting spatial resolution. So far, we've assumed that in all of these insulator materials and semiconductor materials that we've analyzed, that we've looked at so far, all of the photons that are generated escape the sample to be detected. That's not always true. It is true generally in a transparent material that all of the photons that we collect or that are generated by the electron beam pass through the sample and escape into the vacuum for us to be able to detect with our CL detector. However, a significant number of samples are opaque or at least semi-transparent. And in that case, you have to start thinking about photon reabsorption before photons escape. This is particularly the case in metals. And in metals which are incredibly opaque, photons actually only escape from a metal from within a parameter called the skin depth of the material, so very, very close to the surface, within 10 nanometers typically. So any photon that's generated within the sample below the skin depth is reabsorbed before it's able to exit the sample, and so we don't have to worry about any of the electron-specimen interactions that take place below the skin depth level. And now the image resolution is limited effectively by the skin depth of the material. And we can see that in this next image, or this series of images that I show you. This is a collection of metallic nanoparticles. They're quite small, 200 nanometers in size. We have collected this cathodoluminescence map on the right-hand side using an accelerating voltage of 20 kV. Now, from the modeling that we did earlier, we know that an electron beam at 20 kV should have interactions with the sample over the whole particle. So the whole particle is being excited everywhere in it. However, when we look at the cathodoluminescence map, we see these bright points, so these hot spots where strong light emission is taking place at the tips of this nanostar. And those bright emission spots are separated by just 20 nanometers. So we know that the spatial resolution in this material is better than 20 nanometers. And that's purely determined by the material property called the skin depth. The two colors here relate to two different polarization states of the light emitted. It's not important for this discussion, but just in case you were wondering. So to try and summarize up what we've been through in the first part of this talk, really the strategy for getting the sharpest CL images really depends on the type of material that you're looking at. Insulators, ceramics, minerals, gems, ceramics, oxides, those sorts of things. Typically, we like to use medium to low accelerating voltages where we have sufficient signal-to-noise ratio in order to be able to collect maps, a small generation volume, but typically we're limited by the signal-to-noise ratio and sample preparation. In semiconductors, we tend to use the lowest accelerating voltages we possibly can, generally because they are more efficient at emitting light than the insulators, and so we can use these very low accelerating voltages. And here we have to think about minority carrier diffusion, but fortunately, in a lot of cases, the sample structure actually helps us. And again, typically, we run into the case where we become signal-to-noise ratio limited. In metals, we have a slightly different approach, and here we tend to prefer to use high accelerating voltages as we're able to generate more photons per incoming electron at high accelerating voltages to gather better signal-to-noise ratio maps. And then there are a couple of materials properties that we have to think about also that determine and drive the spatial resolution we can achieve, so the skin depth of the material and the propagation of the surface plasmon polaritons, which are the wave setup as the electron specimen interaction to absorb the energy. So your specimen or your type of specimen has a very strong impact over the way you set up your microscope in order to be able to collect the sharpest CL images. In all of these cases, signal-to-noise ratio is a real challenge, and there are several things that, or not just a real challenge, but are probably the limiting factor in the end for how sharp an image you can collect. And some of that is simply related to the light emission efficiency of your samples, the number of photons that are emitted per incident electron. And the other is the probe current of the microscope. Not the brightness of the electron source, but the absolute probe current, so the number of electrons that arrive at your specimen. The other thing that is really important is the sensitivity of the detection hardware that's used, because that has a direct impact on the signal-to-noise ratio. We'll speak a little bit more about that in the second half of this presentation. Let's move on to that now. Let's think about how we collect or how we detect the emitted photons. So we think about the collection and the detection system that we're going to use. Now, in many materials, the electron beam comes in and strikes it, and the light is emitted isotropically. It means it's emitted in all directions. So it's like a light source being placed at the very center of the Earth and light being projected into the northern hemisphere and into the southern hemisphere. However, especially in an SEM, the sample is thick. There is a sample to be able to move it around. And typically, light only escapes from the specimen into that upper hemisphere, which is represented in the center. And a different projection, now looking down from the top, is shown on the right-hand side, so the azimuthal projection of the northern hemisphere. So we, to improve or to achieve the best signal-to-noise ratio that we can, we need to collect as many of the photons that are being emitted from the specimen as we can. And typically the way that this is done in the most efficient manner is to use some sort of collection or a collection optic, an objective that covers a large solid angle and reflects the photons that are emitted from the sample into detection hardware downstream in order for us to be able to analyze the light that is emitted. In the latest generation of spectroscopic CL detectors, for example, the Monarch system, we can collect something like 85% of the emitted photons using a high numerical aperture collection optic. And I've indicated on the map on the right-hand side, where I've shaded out the regions of that angular space in the northern hemisphere, which we can't collect. But this is sufficient that we can collect something like up to 80–85% of the photons emitted from a Lambertian emitter. So this allows us to maximize signal to noise ratio, which is really important, remember, for getting the sharpest images. And it also allows us to reduce electron dose so we can avoid beam-induced artifacts. So once we've collected as much light as we possibly can, it's important to design an optical system with very high efficiency. So all of those photons that we collect get through to our detector at the other side. Let's take a very simplified look at the ray diagram of a typical CL imaging system. So at the bottom we have a sample, and then we have the collection mirror, which can be represented by a simple lens. Then often some transfer optics, which take that light and couple it efficiently into a detector. Now, light that's emitted at on the optical axis and at the focal point of the collection mirror reaches our detector with very high efficiency. Now, our detector then puts out an intensity measurement or counts. So we can detect the number of photons per second being emitted from this point on your sample. We would then scan the electron beam to form a CL map, either at total intensity, unfiltered CL map, or a wavelength filtered map, depending on the transfer optics and the way that you analyze the light in your detector. However, as you scan the electron beam away from the center of your optical system, you end up with photons being emitted from your specimen which no longer arrive at your detector efficiently. This is an effect known in optical systems as vignetting. And many of you who will have used mirror-based CL detectors previously will be aware of this in terms of the sweet spot or the hot spot. So there is a certain focal range over which light is collected very efficiently in these systems. Then outside of that, the photons that are emitted from the sample are readily lost, and the intensity in an image drops down dramatically. So it's really important to maximize the sensitivity of the CL systems so that we can get the best signal to noise ratio images and the sharpest images, the best spatial resolution, to be able to position the sample in the sweet spot of the collection mirror. So there's actually several things that you need to align in order to be able to have this very efficient coupling of light from your sample into the detection hardware. The specimen needs to be located at the precise focal point of the collecting mirror, and the optical axis of the CL mirror or the CL system as a whole and the SEM need to be co-aligned with pretty much micron precision. So we need to align the CL mirror in X and Y to the scanning directions of the electron beam axis. And the important thing to note here is that this alignment of your microscope, or the center of your scan pattern in the microscope, is accelerating voltage dependent. Every time you change the accelerating voltage during a session, you actually need to realign your CL system to the microscope in order to continue to collect light efficiently. We then also need to be able to place the specimen at the focal point of the collection mirror, the CL system as a whole, and easier is to focus the electron beam at the sample region of interest. Now, historically, this alignment has actually been really difficult to do, and many users have not been able to get the best results out of their specimens simply because they've been unable to align these different parts of the system. Now, one of the things that, so Gatan recently, or in the last year or so, announced a new generation of CL detector called the Monarch system. And this is a problem that we were very aware of and realized that needed to be addressed to make everybody who uses CL systems successful. And so we came up with a way of the system auto-aligning itself, not relying on the user to be able to do any of these operations. And by doing that on all specimens, the Monarch system automatically aligns itself, delivering much, much greater precision in its alignment, even than an expert operator, even better than I was able to do myself, despite using these systems for 20 years. And this allows us to collect and detect many more photons than we were able to do previously. So an example of that is shown on the next slide, where we have two data sets, one acquired with an old CL system that's not been able to be aligned perfectly, and the Monarch detector on the right. Now this is a two-dimensional material, incredibly thin, emits with very low luminescence intensity, and so it's incredibly difficult to align. However, with the Monarch system, the alignment happens independent of that process and independent of the user's ability to do it. And so everybody on the right-hand side who came to use the Monarch system could collect results like this. The sharpest CL images for all users, because we've been able to align the system correctly, achieve the best signal-to-noise ratio images, and understand the best operating parameters for the microscope. Okay, so that's spatial resolution covered. There are lots of other analysis modes available with modern day CL detectors, and so I'm going to cover some of those in the remainder of the talk. And the first type of analysis that I'm going to cover is spectroscopy, so capturing the sharpest CL spectrum, and also spectrum images, which is or hyperspectral data, which is a type of data set where we have all of the spatial and spectral information contained within a single data set. So, to capture or to analyze the wavelength distribution emitted from a specimen, we use a spectrometer or a spectrograph. So this is a simplified ray diagram, this time turned 390 degrees. Your sample is now on the right. It's an optical system that collects the light emitted from your sample and sends it to a spectrograph. And the spectrograph analyzes the wavelength distribution of the light that's emitted to form a wavelength resolved spectrum, so intensity against wavelength. And it does this by using a series of optical components that act to disperse the light by wavelength and refocus it onto a detector, with now one axis being wavelength. So we've resolved the wavelength information within our light, and we're able to capture a spectrum. Now, there are several key components within the spectrograph that govern the spectral resolution of the end result. So first of all, the optical design of the spectrometer is a really important part of it. Configuration, which means the way that all of the optics are laid out, and there's various different reasons why one configuration is preferred over another. The focal length, the size of the optics, whether it's an aberration-corrected optical design, there's many, many parts associated with that. However, generally, these are fixed components of a system that you already have and not something that you can do something about as a user. I will come back and speak to you quickly about the differences between older generation technologies and the Monarch in terms of this optical design, but it'll be very brief. There are two things that as a user we can do or three things that we can do in order to guarantee that we have the sharpest emission spectra that we can. The first is optimizing the entrance slit width to the spectrograph, so the entrance aperture. The second is choosing the appropriate diffraction grating, the element that is responsible for separating the light wavelength. So let's first of all start by looking at the size of the effect of the entrance slit on spectra that we record. So this is a cathodoluminescent spectrum from a phosphor powder. It doesn't really matter exactly what the material is. I'm going to show you a series of spectra with sequentially narrower slit width. So we start off with a 1 millimeter wide slit width, and we have some spectrum with a series of peaks that you can observe. And as we start reducing the size of the slit width, we can see that we can start seeing much finer detail within the spectrum. So at wide slit widths, the instrument was smearing out the wavelength information. We had insufficient spectral resolution to observe the fine detail that was there in the emission spectrum. The narrower slits deliver higher spectral resolutions. We can see that if we look at an overlay of those 4 different slit widths, 4 different resolutions, and compare them. On the right-hand side, you can see them normalized by the maximum intensity. And you can see that we see more detail in the spectra which are captured with narrower slit widths or higher spectral resolutions. Importantly, though, you also see that the peak positions become more accurate. So we have data that we can trust more. The other spectrum, or the other series of spectra on the left-hand side, show you that as we narrow the slit width, we actually have a significant reduction in the intensity in our spectrum. And this is important. So we want to be able to use wide slit widths if we can to get as much light into and through our spectrometer to the end result, but only enough, but we still need to be able to get the spectral resolution to enable us to observe the features that we want. So there is a trade-off between having enough light and being able to have the spectral resolution needed to observe the information in the spectrum that we need to observe. The other thing that we can change as a user within the spectrograph is to select a particular diffraction grating. Many spectrometers come with a selection of 2 or more diffraction gratings, and there is a parameter of diffraction gratings called its ruling density, and the ruling density controls the dispersion, i.e. how well a particular diffraction grating separates the light into its component colors, so how far they're spread out. You can see we're comparing 2 diffraction gratings in a schematic representation on the left and right hand side. And in the high ruling density grating, we have spread out the light much more, gives us higher spectral resolution, but a narrower range of wavelengths falls on our sensor. So there's a trade-off between high spectral resolution and the wavelength field of view. So typically we try and use low ruling density gratings if possible, as long as they provide us sufficient spectral resolution and allow us to use large enough slits. Now, understanding that alignment was important for the images is one thing. Alignment is perhaps even more important for spectroscopy results than for the imaging results we looked at earlier. So here is that schematic diagram that we're now focusing light onto the entrance slit of the narrow entrance slit of a spectrograph. And a spectrograph is the thing which gives us our wavelength spectrum. Now, the entrance slit to the spectrometer could be set as small as 10 microns, in which case our transfer optics require us to focus the light down to as small a spot as possible so that as much of it goes in through that 10 micron slit as possible. In order to do that, the optical alignment of the sample to the CL system and all of the optics within the CL system have to be to allow us to get the smallest spot entrance slit possible. And to ensure that all of the wavelengths of light are focused at the same point, i.e. at the entrance slit, the optical system should be free of chromatic aberrations. We tend to prefer to use reflective mirrors rather than using transmissive lenses. Let's take a look at how that alignment directly affects the amount of light we're able to get into a spectrum. So here, these are spectra captured with the Monarch detector, and the solid green one that says in focus is directly after the Monarch system has done its auto-aligning process. So this is what you turn the system on and you align the system and it presents you this spectrum. We are then going to intentionally misalign the sample by increasing the spacing between the collection mirror and the sample. And you can see that as we increase that spacing in just 20 micron increments, you can see this dramatic drop-off in intensity in the spectrum. So an optical misalignment of just 20 microns in one direction results in a 50% loss in the signal. So you can really see why alignment and being able to get perfect optical alignment is such an important thing in CL microscopy. Now, I mentioned earlier that the Monarch detector has a different optical design to what was done previously in conventional CL spectrographs like the Monocle 4. The Monocle 4 was a Cherney-Turner configuration spectrometer, and in that type of detector, or the light that goes into the spectrometer does not get imaged perfectly onto the detector. There are aberrations. When we look at a series of spots that have been imaged through the system at the edge of the sensor, you can see that rather than nice round spots being imaged on our detector, they've actually been elongated through aberrations into these ellipses. This loss in intensity means that we have peaks which are broader and less intense. So we have poorer spectra as a result of it. Now, the Monarch system and the Monarch Pro system in particular has an aberration-corrected spectrograph that allows us to get these sharp images across the entirety of the sensor that we use to collect images and spectra. So we have almost no astigmatism left in the spectrometer. We have this aberration-corrected spectrograph, and it means that we have the sharpest images or spectra across the entire CCD. What this means is that when we look at the spectra from these two different types of spectrometer, we see that the Monarch system, with its improved optical design, has significantly taller and sharper measured from the same specimen. So we have much higher spectral resolution and much improved signal to noise. And one of the things this allows you to do is to operate the Monarch system with a slit width which is much wider than in previous generations of detectors, and to get the same amount of, so operate it with much wider slits to get the same spectral resolution, but a very significant increase in optical throughput, so the amount of light that ends up in our spectrum. When you're collecting just a single spectrum like you are here, that probably doesn't make a great deal of difference because you're just talking about a saving of a few milliseconds or a few seconds, and at most a few tens of seconds. But if you're performing hyperspectral imaging or spectral imaging where you're collecting many, many spectra, so for example, in this data set here, 30,000 spectra, that decrease in acquisition time that you can achieve using this improved optical design spectrometer means that you can perform spectrum imaging data, collect spectrum images much, much faster than you were able to with previous generation of technology. This is a big improvement in being able to collect sharp spectra and sharp hyperspectral data, so spectrum images. Okay, so I'm going to go on to the last section of the talk now, and this is a new analysis mode that's been enabled by the Monarch detector, and it allows you to collect angle-resolved CL patterns. So we're able to detect the emission patterns emitted from a sample. Rather than collecting the light, sending it through some transfer optics onto a detector that measures intensity, in that angle-resolved mode, we change the transfer optics and the detector, and this time we form an image at the sensor. So we see an image of the light projected from the back of the collection mirror. And I'll show you that in a little more detail here. So here is the light coming through the collection mirror, being reflected off of the mirror onto our array detector. Now, each pixel in this image on our array detector corresponds to a unique emission direction. A photon emitted in a particular direction ends up at a certain pixel in our detector. And we can calculate back, remap into angular space the direction in which light was emitted. As you see here, this is the light emitted from that nanoparticle, actually, that metallic nanoparticle that I showed earlier in the presentation with the two different polarizations. You can see that we have completely different emission directions depending on the polarization of the light. This is one of the interesting things about this type of work. Now, this type of analysis mode was actually developed developed initially at Tokyo University in a TM, and then extended further in Amsterdam by a group there using a home-built CL system. And this data shown on this slide comes from the thesis that was written about. It shows nicely how the image that you see here is projected nicely back onto an array detector. You can see the physical extent of the mirror, and all of the light falls within that, and so we can map perfectly back to the emission angle. However, a small misalignment easily destroys that relationship between the pixel coordinate and the emission direction. And misalignments simply as small as 5 microns mean that you prevent the angular information from being recovered. So, bring the sharpest emission patterns or angle-resolved information requires you to have the perfect optical alignment. We thought about this a lot when developing the Monarch system. One of the downsides of having this strict requirement for this perfect alignment is that it becomes very fiddly. Operators take a long time to learn how to do this, and even then they have a very limited field of view, because as soon as you move more than 5 microns away, you destroy this relationship between the pixel in the image and the emission direction. So in the Monarch system, we spent a lot of time thinking about the transfer optics, how we transfer information from the back of the collection mirror to our detector. And not just in the angle-resolved mode, but in many of the operating modes. So for example, here, this is the unfiltered image, and you can see that we have a field of view extending over hundreds of microns. Here, the full width of this image is 700 microns, and you can start to see vignetting edges. This is a big improvement compared to the Monocle 4 that some of you may be used to. In terms of angle-resolved information, these are, on the left-hand side, is a 4-dimensional data set, so an angle-resolved spectrum image where each of the pixels in this data set contains one of these images that contains angular information. So here I'm demonstrating a field of view of about 5 by 5 microns, i.e. what could have been achieved using that system developed in Amsterdam. With the Monarch system, though, we thought very carefully about the transfer optics and came up with a method of dramatically increasing the field of view, increasing it by a factor of 400. What this means is that we can collect these sharp, perfect angle-resolved emission patterns over very wide, large field of view without losing this angular information. So if I just extract a couple of the projected images from this 4-dimensional data set, you can see even far away from the optical center, we still have a perfectly aligned image. So this allows us to produce these really sharp angle-resolved emission patterns over a much wider field of view. When you do that, it becomes actually very simple to set up the experiment, especially with auto-aligning help. And so you can collect an angle-resolved emission pattern like this. This is a emission pattern that's being sent through an angle selecting grid, so a mask that prevents certain angular ranges from being blocked. These types of images where we have better than or approaching or better than 1 degree angular resolution are achieved within just a few minutes of turning the instrument on. The other thing that the Monarch system does is allows you to analyze the emission patterns spectroscopically, so a technique called wavelength and angle-resolved CL. And when you do that, you collect emission patterns at full spectral resolution. So you can think of it as having up to 1,340 emission patterns, each at a different wavelength, all being able to collect an emission spectrum in any given emission direction. Now, what I've presented, or my colleague Jonathan has presented this data in a separate webinar, and I encourage you to go and read that or listen to that webinar, webinar number 2 in the Cathodoluminescence Explained series, where he talks about using this technique as a way of characterizing a micro LED array that's being developed for display applications. Okay, and with that, I'm going to summarize. So capturing CL data with the highest spatial, spectral, and angular resolution, it depends on many, many factors. That's one of the challenges that makes performing CL complex as a user, is that there are so many factors that you need to be able to think about. You need to think about the electron specimen interactions and processes that take place within the sample in order to be able to determine the appropriate operating conditions microscope for your specimen. Really, really importantly, and I'm sure I emphasized this a lot during the talk and continue to do so, is that it is critical that you align the systems well. That's the CL system to the microscope and the sample to the CL system. And you do that at each and every accelerating voltage. And you do this so that we can maximize the signal to noise ratio, which is often a limiting factor to high resolution results. We can reduce the electron beam damage because we can collect more photons per incident electron, and also ensure that all of that angular information can be recovered. The other thing to say is that when we operate the spectrograph to get high spectral resolutions, we should be selecting slit widths and dispersions that are sufficient to allow us to observe the natural emission spectrum from our sample. So optimize the slit width for the spectral resolution needed to observe all of the information within a specimen. With that, I'm going to remind you that you are able to submit questions using the question pane on the right-hand side of your screen. Just type them in there and press send. Any remaining questions that I don't have a chance to answer, and I think we're probably almost out of time, will be addressed offline. Recording of this webinar will be available within 5 business days and will be posted to the Gatan. If you've registered, or you must have registered, a download link will be provided to. And also, please take the time to suggest topics of interest for future webinars. So the next webinar we're planning for January, late January, maybe early February 2020. And sorry, that title is incorrect. It should read how to interpret or support in interpreting CL data, and particularly CL spectra and CL spectrum images. So with that, thank you. And I think we probably have time just for one question. So let's take a look. Okay, so the first question, or the question that's happened a couple of times actually, does the spatial resolution improve if we use a TEM rather than an SEM to analyze our specimen? Well, the answer is potentially. Many of the topics that I discussed in terms of the electron sample interactions and the processes that go on within the sample hold equally true whether you're dealing with electrons from an SEM or a TEM. The advantage that a TEM has over an SEM is that because we're using electron transparent samples, so very thin samples, when the incident electron hits the specimen and interacts with it in some way, it very soon after leaves the specimen, and so it doesn't have a chance to spread out within the sample. So we overcome many of those interaction volume limits that we talked about earlier in the presentation. Now, the downside of this is that we have very few photons produced per incident electron, and so the range of materials that are suitable for being analyzed in the TM is much smaller, probably limited to direct bandgap semiconductors and probably nanophotonic materials. But certainly in the TM, people have been able to demonstrate spatial resolutions approaching or around 1 nanometer rather than the 10 nanometers or so that's possible in the SEM. Okay, and with that, I think it's probably time to wrap up. As I said, any more questions I will answer offline. So thank you for attending today or downloading and listening to this at a separate time. Thank you.